This is the second video for looking at 6.1 rates of reactions. So now we're going to be looking at the energy involved in what is going on the atomic or molecular level with the atoms and the reactants and the compounds. We're going to be looking at the kinetic molecular theory, which still spans biology and still spans physics, but we want to know what's going on with the atoms themselves. So the kinetic molecular theory are the particles in a substance move randomly as a result of kinetic energy. And because we're looking at energy, we are looking at the amount of energy based off temperature. When you're looking at the kinetic molecular theory, we are using the average kinetic energy in relation to the absolute temperature. And remember, absolute temperature is a measurement on the Kelvin scale. So just as a diagram representation, and hopefully just review. So if we have a scale, and what we're doing over the course of this scale is if we are increasing your temperature, we would then therefore expect to increase the amount of kinetic energy, right? So now let's look at the molecules. When we're moving through, so if we have a solid and we're going to increase the temperature, we therefore expect to see an increase in kinetic energy. Well, that's going to start to break down the crystalline structure of a solid. And then we expect it to take a phase change into a liquid, which now that has more energy and the ions are starting, or the molecules are starting to flow. Whether we are breaking forces or we're breaking bonds, it all depends. And that's going to differ from every compound, how much temperature and kinetic energy needs to be present. But if we continue to increase that, we then expect that liquid to phase into a gas. And then, of course, you can continue to heat up a gas in a closed system to study the properties of those gases. And, well, that's what Maxwell and Boltzmann did. So we created the Maxwell-Boltzmann distribution curve, and this looks at gas behavior and looking at what are different things that affect gases. Because as we discussed in topic 5 of energetics, is we break and form bonds, and we measure the energy involved with breaking and forming bonds when atoms are in their gaseous state. Therefore, if we're looking at the amount of energy involved there, and the motion that is occurring, we would expect to run it at the gaseous state as well. And so Maxwell-Boltzmann created a distribution. And here's what a Maxwell-Boltzmann distribution curve. You absolutely need to be able to draw this curve. Now, it doesn't have to be absolutely perfect like this. Mine are nowhere near this well done. But you need to be able to at least draw it to represent what's going on in a reaction. So the Maxwell-Boltzmann curve show the number of particles that have a particular kinetic energy. So please look at the y-axis. The y-axis is quite literally the number of particles with kinetic energy. And so we're seeing an increasing energy as we go up. And then on the y-axis, we have kinetic energy. As students have been asked this question in the past to draw a Maxwell-Boltzmann curve, and they don't label the axes, which means there's 1 or 2 points. Now, what is represented by a Maxwell-Boltzmann curve is that what we're looking at is the area under the curve, actually. And so if we look at the area under the curve, this whole area, that is going to give you the total number of particles in a sample. And then, of course, we can say how many particles have kinetic energy at this point, right? And then everything above it has that kinetic energy. And because we have the number of particles going on in that reaction, we can now quantitatively determine how many particles are running at what energy rate. How do reactions happen then? And there's a nice little diagram. So first thing that has to happen, our particles are going to collide. All right? And if you look here, A and B are colliding, right? And when they collide, there creates an instantaneous interaction. And depending on the strength of that collision, that interaction may eventually overcome the original one that B and C had, and therefore B and C break apart and A form a bond. So we are breaking this bond right here between B and C, and we are forming the bond between A and B. So some bonds are broken based on the energy provided in that collision, and then some bonds are going to be formed. And you guys know how to calculate this from the last topic. And so therefore, the rate of reaction is the number of successful collisions, and therefore the creation of products that then we could then measure. So how can we predict how successful a reaction is going to be? We need to look at what influences the rate and influences whether or not a reaction takes place. There are two factors we're going to look at. The first is the energy of a collision. How much energy is there when two particles collide? Well, first, in order to break a bond, the particles need to meet or exceed that activation energy. And activation energy is the minimum kinetic energy needed for a reaction to take place. So we get to that activation energy, and that is going to be necessary for overcoming any repulsion that is occurring or breaking bonds before a reaction is going to take place. Therefore, those atoms or those molecules need to overcome that energy barrier. And once they do that, the reactants achieve a transition state. And during that transition state, you start to get product formation because you have broken any bonds that you need to, and that allows those atoms to be available to allow those bonds to form. So what this looks like, if we go back to an enthalpy diagram, right? And so just to give you an idea of what's going on. So here we have our reactants. Here we have our products. As we know, this little hump, right? That is your activation energy, and we shorthand it as EA. And we know the overall distance from your reactants to your products is your change in enthalpy. So only particles with the kinetic energy, because E is at our Y, so only particles that reach this hump have enough energy to have successful collisions. Collisions with enough oomph to break a bond or get over repulsion in order to form new bonds. So this peak, that's that transition state that we are looking at. So when we are looking at the fact that rate is the portion of particles, or number of particles, I can spell, that have the kinetic energy greater than or equal to your activation energy. All right? And so before we go into geometry, I forgot to draw. If we have our Maxwell-Boltzmann curve, okay, we have, and I told you I was really bad at drawing these, right? So we're looking at the amount of energy, right? Here's our EA of our kinetic energy label. So these guys right here, all these particles up here, these ones have the kinetic energy greater than or equal to your EA. So they are going to have successful collisions. All these atoms here on the other side, their kinetic energy has not reached that of the activation energy, so they are less than the activation energy, which means there are no successful collisions. There's not enough energy to break bonds. Therefore, we should expect no product formation. And this way we can theoretically predict how much products are we going to get depending on how many particles are above that activation energy barrier. And so industry therefore is able to determine how much we should be able to expect at what temperatures, what pressures, everything along those lines, and therefore what do we need to do to manipulate our reaction to benefit our production of product in industry. Okay, sorry. Now looking at the geometry of a collision. So because gases are moving randomly, and all atoms are moving randomly except for in their solid state, they're all going to have different orientations. And based off that orientation, they're going to have a different success at the rate of reaction, or for a reaction to take place. So in A, we can see that our orientation of our atoms, when they hit, they're not properly oriented to break the bonds in between each. So they're just going to bounce off each other and you're not going to form a product. But when they are properly oriented, where you can see where the bonds will align that then allow a new bond to form, you can therefore start to get products. So you have to have the right alignment. So there are factors that affect rate. How can we manipulate that kinetic energy, and how can we manipulate making sure our particles have the correct geometry, so on and so forth? Temperature, of course, is going to be the easiest one we can go through and look at. So here we have two Maxwell-Boltzmann curves. Now we know, and what we theorize is if we increase temperature, right, we are going to increase the average kinetic energy of all the particles in our reaction. That makes sense, right? So if we're running a reaction at 300 K, and then we're going to run a reaction at 310 K, you can see that the entire graph has shifted, right? Which means that at the 310 K, based off the area under the curve, you have more particles with an increased kinetic energy. And that's what gives you the shift. So if we go through and we put our activation energy site, right? So here's our EA. Originally, we had a certain number of atoms or molecules that had enough energy to perform the reaction. But because we've increased the energy of all our particles, the amount of area under the curve has also increased. So now we have increased the collision frequency because more particles have more kinetic energy, and therefore they're moving around more erratically. So they're going to hit each other more often. And because they have enough energy, we're going to increase the number of successful collisions. And this is going to increase your rate of reaction. And so that shift in temperature changes the proportion of particles that are available at the activation energy. Now there's a rule of thumb, it's not for every reaction, but it's a rule, that you double the reaction rate every 10 degrees Celsius, and we are going to look potentially at those kind of calculations a little bit later. Another factor that can affect rate is concentration. So if you increase your concentration, you are going to increase your rate. Reason being, if you look at our diagram, so here we only have 3 little guys, right? And you're like, oh, so sad, there's only 3 there, only 3 at the party, right? Now we have a whole bunch, okay? And because there's more there, there's more potential for an interaction to happen. And since there's more potential, you're going to have an increased frequency of collisions, and therefore you're just increasing the chance of a reaction occurring. The next one is particle size. So think of a cube of sugar versus a grain of sugar, and if you try to throw them into tea, how fast it dissolves. And what I've never understood is why Like in England and on TV shows, they're like, do you want 1 cube or 2 cubes of sugar? And I'm like, why? It's going to take forever to melt it anyways. Why don't you use like spoonfuls of sugar? I never got it. But anyways, if you decrease your particle size, you're going to increase your surface area that is available. And if you're going to increase the amount of surface area, and therefore you're going to increase the number of reactants at the surface available for a reaction, you therefore should increase your rate. And so that's going to allow for more contact and a higher probability that you're going to have successful collisions. Again, don't understand why people say let's use cubed sugar. I don't get it. What's the point besides building things? Next, looking at pressure. And pressures involve gases. So if we're going to increase our pressure, and that's what this diagram is showing, that by pushing down this lid, we're increasing pressure, right? Well, that means the atoms have less space to move around. And if you have less space to move around, you're increasing your chance of an interaction, and therefore you're increasing the collision frequency, and theoretically, you're increasing the concentration of atoms per volume. And based off that, we would expect an increase in your rate of a reaction. So the more pressure there is, the more reactions should theoretically occur until there's too much pressure and too much temperature, and of course, then it all busts open. And then lastly, a catalyst. So hopefully this is a reminder, but a catalyst is a substance that increases the rate of reaction without itself undergoing the reaction or being permanently changed. So it's not doing anything except helping push a reaction forward. Most provide an alternate route for a reaction, and they do that by decreasing the activation energy. So if we have our enthalpy diagram, and we talked about this in topic 5, and we have our reactants, and we have our products, and we have our pathway. And so our activation energy is the hump, right? Well, we expect a catalyst to lower that hump. So we could sketch a Maxwell-Boltzmann curve to represent this. Again, told you I was no good at this. So we had our original activation energy, which has the number of particles that are going to react. But because a catalyst can provide an alternative route for the reactants, whether they're aligning them up for a proper interaction, so geometry, which is what enzymes do, you could also just be increasing the temperature within that reaction, like applying heat, and therefore more particles are available. It all depends on it. But what happens is you are going to change that activation energy. And so you're not shifting the graph at all. That's if you're increasing temperature. If you're adding a catalyst like magnesium dioxide, or you're using an enzyme, whatever it happens to be, you are changing the value of your activation energy. And so your particles don't necessarily have more energy, but you have more particles at a lower, or you have more particles at the lowered activation energy. All right? So something to keep in mind is that a catalyst will affect forward and reverse reactions equally. And they do not affect the overall yield, just the time to get to that yield that we would expect if we just allow a reaction to run at normal rate.